Okay, unit 2 is all about differentiation. The derivative it just means the slope of a point. So how can you find the slope of a point if you need 2 points to find the slope? That's why you need limits, and the limits allow you to find derivatives. So you're able to find the slope at a point. Again, this is called the derivative. You should know that. Slope of a tangent line, slope of a point, it means derivative. Okay, 232. This is just a preview. We're going to start doing example problems in a little bit. But 232 is all about the differentiation of parametric functions. Now, you should understand parametric functions from pre-calc, but some of you might have not taken pre-calc for years. So I'm going to do a review of what a parametric function is. It's actually not that complicated. It's based on a parameter. In this case, the parameter is t. They always use t for some reason. So what I'm going to do is I'm going to graph this right here. Let me. How can I break this down? I think I have it right here. Okay, so with parametric, your x is defined based on some function with t as the input, and your y is based on some function with t as the input. Usually the x and the y are related to each other, like y equals x squared or y equals x minus 1. The y and the x are together. Here, they're separated, and you use the input as a t. Okay, so it's almost like you have a third variable, but you can still graph the x and the y, and that's what I'm going to show you right here. Here, let me blow this up. This first thing right here is basically coordinates based on t. So this is an x, this part's the x, and this part's the y. Now, if you put in different values of t, in this case, I'm going from a to b. This is a to b right here. For t, so for example, I can put in a is -5. So if I can put -5 in here, and then I put it in here, and you get some value spitting out, and then it would graph that x and y value. So what does that mean? Let me show you with a graph. So let's do this. Oops, zoomed in too far. So if you change the a to b and the a and b values for t, it just starts plotting out points. Okay, so you're using the x and the y is defined by some t. In this case, the t is from -5 to 5. And it makes a little graph like this. That's literally the only thing that's the difference between a regular equation and a parametric. You can turn a parametric equation into a regular equation. As you can see, it lines up exactly with it. All you have to do is solve for t and substitute. We don't need to worry about that though. But that's what a parametric is. And if I wanted to, I can pick different values. So if I wanted to pick 10, it would just keep going. Again, it still lines up if you solve for t, but you don't need to worry about that. Okay, so that's parametric. There's an extra variable basically. Okay, now this allows you to go thinking, why do we need this? It allows you to do certain things you can't do in a y equals x graph. For example, if I have this cosine, so I'm graphing cosine t for your x and sine t for your y. So x and y, that's basically the unit circle. So if you actually graph this out, it should form, whoops, way zoomed in here. If you graph this out, it actually forms, if you go all the way to 2 pi, it forms the unit circle. The unit circle is actually a parametric function, or I'm sorry, a set of parametric equations that, but they don't really use the word parametric sometimes to explain that. But the only way to make a circle like that, well, not the only way, but the easiest way to do that is with parametric. That's what this is here. And then you can also do something like this, where I made it like weird equations, weird expressions for the x and the y, and then as you change this, it ends up forming some cool little pattern like that. And again, it's the same thing that you've already been doing. It's just with a t. You don't need to know the basics behind parametric so much as you need to know how to find the derivative using a parametric. And that's basically what this whole section's about. There's a formula for it. This is actually the second derivative. I'm not going to worry so much about the second derivative part. This first derivative, though, is going to be important. And basically, you're just doing the derivative with respect to y over the derivative with respect to, the derivative of y with respect to t divided by the derivative of x with respect to t. And you can see the dt's are basically going to cancel. So you end up with the derivative, which again is just basically the slope of one point, change in y over change in x. That's the slope. The second equation is the second derivative. That's parametric. We're going to be using these formulas in a little bit. I just kind of wanted to introduce what a parametric is or reintroduce it and then talk about how we're going to use it. All right, so 2, 3, 4 is all about derivatives of polar forms. Okay, this was derivative of parametric. With parametric is with a t. There's a parameter t. This one is polar, and you probably forgot what polar is if you haven't had pre-calc in a while. But basically, with polar, you in pre-calc or trig or whatever class it was, you had to convert the rectangular coordinates, the x and the y, into circular coordinates or polar coordinates. It's called. So x is equal to r cosine theta, y is equal to r cosine theta. Now this is basically the unit circle. If the radius was 1, x is equal to cosine, y is equal to sine. To find the derivative of this, you just do, it's actually really similar to parametric. You do the derivative of y with respect to theta and then x with respect to theta, and you just divide them. The d thetas cancel. Again, I'm going to show you examples of that. But first, let's review what a polar graph even is. The way a polar works is it's still on an XY coordinate plane. If you can see, like this is still Y, this is still X, but it bases it off circles. So polar graphs are used for any time you like study something in space or because there's orbits. Anytime you study something that moves in circles, you're going to want to use polar graphs. It's just easier because, as you can see right here, we have a unit circle. Its radius is 1. So here's the origin. It goes up to 1, and it goes 1 in every direction. You can just say the radius is equal to 1. That's what this says. Let me blow this up. Say the radius is equal to 1. If you wanted to do that with rectangular coordinates, you'd have to write all of this out. And you get the same, let's change the color here. You get the same, let's do blue. You get the same answer here. As you can see, it directly overlaps. But it's a lot easier to write it this way. And if you're going to be doing math with this, it's a lot easier as well because it's just with radius and theta. And then I just thought this is cool. If you actually take the radius and set it equal to what the theta is, as it goes around, your theta is increasing as you go around. And that's also the radius. So your radius is actually equal to the theta. So it actually forms like a cool little spiral thing. It's called the Archimedes spiral, I believe. And I only went to 12 pi. I could have this out for a bunch, but I don't know. I just thought that was cool. I don't really know why I'm showing that, but that's the main thing with polar. Again, you don't need to know the specifics behind it so much as you need to know how to find the derivative at certain points, and we'll go over those examples in a little bit. So that's parametric and polar. We're just going to be doing the derivatives of those.